You've been walking for 4 days. The camel behind you stopped complaining 2 days ago. That's not a good sign. The Gobi will not warn you. It just takes things. First the feeling in your fingers, then the moisture in your nose, frozen before it can drip. The wind doesn't howl out here, it presses. Flat and constant, pulling heat from your body like a slow drain. The temperature is below -20 degrees Celsius. The wind makes it feel closer to -40 degrees Celsius. Then you see it. A low mud wall rising from the desert floor. A gate. You push through and the wind stops. The air inside is still, warm. A merchant is asleep on a raised brick platform. Coat folded beside him. No fireplace, no chimney, no woodpile. Outside, the Gobi is killing everything it touches. Inside this mudroom, a man is sleeping with his arms out. That's intelligent engineering, and it's been sitting in the desert for over 1,000 years. The city is called Gaochang. It sits in the Turpan Basin in northwestern China, and it is one of the most extreme places humans ever chose to build a permanent home. Summer ground temperatures hit 70 degrees Celsius. Winter nights drop to -20 degrees Celsius, sometimes colder. Annual rainfall is approximately 15.7 millimeters. The Sahara gets roughly 25. Turpan is drier than the Sahara, hotter in summer, and cold enough in winter to kill you in hours. And yet, around 750 AD, Gaochang was a busy Tang Dynasty city. Thousands of people lived here, merchants, monks, soldiers, families. The Silk Road ran straight through it. There was no way around. The ruins still stand today. Rammed earth walls, built in 8 to 12 centimetre layers, still visible after 1,300 years of wind, heat and cold. The city didn't fall apart. The people eventually left. The walls stayed. So how did they survive? Not with one trick, with 7 layers of defence, each one solving a different way the desert tried to kill you. And when all 7 worked together, they turned packed dirt, dried dung and underground water into one of the most effective survival systems ever built. Start with the walls. Everything else depends on them. The builders of Gaochang had no stone quarries nearby, no timber in any real quantity. What they had was the ground beneath their feet, fine, pale desert soil called loess, covering the Turpan Basin in every direction. And they worked out something the rest of the world took centuries to appreciate. Pounded earth, compressed into thin layers, is a better insulator than stone. Here's why that matters. Stone conducts heat fast. Press your hand against a stone wall on a cold night, and the cold moves straight through it, pulling warmth from inside toward the freezing air outside. Rammed earth works differently. The loess is full of tiny air pockets trapped between compressed particles. Those pockets slow heat down. The cold has to push through layer after layer of dense, packed material. By the time it reaches the inner surface, most of its force is gone. The technique was called Hangtu. Workers pounded loess into wooden frames, one thin layer at a time, each layer 8 to 12 centimeters thick, compressed until it was nearly as hard as stone. Then the next layer, then the next. The finished wall worked like a slow thermal battery. During the short winter days, the outer surface absorbed what little sun was available. At night, it released that warmth inward, slowly, steadily, smoothing out the wild temperature swings that would otherwise make the interior unlivable. The ruins at Gaochang are the proof. Walk those walls today and you can still see the horizontal lines, each one a single compressed layer. The fingerprint of a builder dead for over 1,000 years. Those lines are still holding. In a climate that cracks concrete, rammed earth has outlasted everything around it. Most people assume simpler materials mean weaker structures. Mud walls sound like something a storm knocks over, but the walls of Gaochang have survived 1,300 years of Gobi wind, 70 degrees Celsius summers, and -20 degrees Celsius winters. No modern building in that region has been standing that long. The material everyone overlooked, dirt, turned out to be the most durable insulator available. Thick walls slowed the cold from outside, but the Gobi doesn't only attack from the sides. Cold air sinks. It pools at ground level, heavy and still, To beat that, the builders went in a direction most people wouldn't think to go. They went down. The Earth has a temperature, not the surface. The surface swings wildly, baking and freezing with the seasons. But go down a few meters and the ground holds a steady, moderate warmth that barely shifts year-round. The builders of Gaochang knew this, not from textbooks, from generations of watching what happened to rooms built at different depths. Archaeological findings at the Astana tombs and residential sites near Gaochang confirm it. Living quarters were often built well below courtyard level, not caves, structured rooms with walls, ceilings, and doorways, but sunk into the ground so the earth wrapped around three sides of the living space. The ground wasn't just the floor, it was part of the heating system. When the surface air outside is minus 20 degrees Celsius, the deep loess a few meters down sits at a much milder temperature. A room sunk into that earth starts warmer before any fire is lit. The earth is doing the first layer of heating work for free. No fuel, no maintenance, no risk of running out. Every fire the merchant lit inside that room was starting from a warmer baseline than it would have been at surface level. The sunk courtyard solved a second problem at the same time. The Gobi wind moves fast and flat. Drop the living area below ground level and the wind passes over it. The air inside the courtyard sits heavy and still, like water settled at the bottom of a bowl. Still air holds warmth. Moving air strips it. The sunk design turned the courtyard into a pocket of calm inside a landscape that offered none. The Astana tombs, a few kilometers from Gaochang, show what stable underground conditions can do. Bodies buried there were so well preserved that silk clothing, painted faces and food survived over 1,000 years intact. The same earth that preserved the dead kept the living warm. The builders weren't just using the ground as a foundation, they were using it as a partner. 2 layers of passive defense, thick walls slowing the cold from outside, sunken rooms borrowing warmth from below. But there was still one enemy that could undo both of them in seconds. The wind, funneling straight through the front gate every time it opened. Every compound had a gate, and every time that gate opened, to let a merchant in, bring a camel through, carry supplies, the Gobi wind came with it. A single blast of minus 20 degrees Celsius air at 60 kilometers per hour through an open gate could strip the warmth from an inner courtyard in minutes. All the thermal mass in the walls, all the warmth borrowed from the earth below, gone through an open door. The solution was a wall behind the wall. Tang-era courtyards placed a Zhaobi, a freestanding screen wall, directly inside the main gate. Anything entering through the gut hit a solid barrier immediately. The wind couldn't travel straight. It had to turn 90 degrees to get around the Zhaobi, and that turn cost it almost all its speed. By the time the air reached the inner courtyard, it had dropped from a 60 km/h gale to a gentle drift. What that created was a pocket of still air inside the compound. Still air holds warmth. Moving air steals it. The Zhaobi didn't generate heat. It didn't insulate anything. It simply stopped the wind from doing what wind does, moving across surfaces and pulling heat away with it. Stop the movement and the heat stays. Wood was too scarce in the Turpan Basin to waste on windbreaks. This was a masonry solution. One earthen wall, positioned correctly, did the work of a windbreak forest. The physics was simple. The placement was precise. And it cost nothing but labour and the same loess already underfoot. Picture the difference. Without the Zhaobi, every time the gate opens, the wind blasts through the courtyard, hits every door, finds every crack, and the rooms lose an hour of built-up warmth in 60 seconds. With it, the wind hits a dead end. The courtyard stays calm. That difference, repeated dozens of times a day across a 5-month winter, is the difference between a waystation that holds and one that slowly freezes from the inside out. The walls held heat. The sunken rooms borrowed it. The Zhaobi stopped the wind from taking it. But none of that generated warmth. For that, the merchants needed fire. And the way they used it was the most precise part of the whole system. Here is the most direct answer to the question in the title. Outside the merchant's room, set into the exterior wall, was a small firebox. Fuel went in, dried dung, scrub brush, whatever was available. The fire lit, and then something unusual happened. The smoke didn't go up a chimney. It went sideways, forced into a network of brick channels called huodao, built beneath the floor and running under a raised sleeping platform on the far side of the room. The smoke travelled through this winding underground path, giving up its heat to the dense brick at every turn, before finally exiting through a low vent on the opposite wall. The platform it heated was called the Kang. The brick lining of those channels absorbed heat slowly and released it back over hours. A merchant could fire the Kang in the early evening, let the fuel burn down completely, and the platform would still be warm at 3 in the morning. The bed was the heater. The fire was just the input. The brick was the storage. Placing the firebox outside the room solved 2 problems at once. It kept smoke and carbon monoxide out of the sleeping quarters, and it kept the fire from burning through the oxygen inside the room. The merchant breathed clean air. The heat travelled in. The danger stayed out. This is the same principle behind every radiant floor heating system installed in homes today. Hot fluid moves through channels beneath the surface and warms it from below. That market is worth billions of dollars. The Kang was doing this in 750 AD, with brick and dried dung, built on 2,000 years of cold winters and careful observation. The Kang is not a museum piece. Families in northern China sleep on Kangs right now. The design hasn't changed because there's nothing to improve. The physics is correct. The execution is efficient. The merchant on that warm brick platform in a mud-walled desert room was experiencing the same thermal comfort a modern homeowner pays a contractor thousands of dollars to install. The Kang heated the room, but a single warm room in the open desert is still exposed. The waystation needed something bigger, a design that turned the entire compound into a shield, using everything inside it, including the animals, as part of the defense. Step back from the individual room. Look at the whole compound from above. A square, high walls on all 4 sides, no windows on the exterior, nothing facing the wind but a flat, unbroken earthen face. Rooms arranged around the inner perimeter, doors facing inward. The outer ring, the space between the rooms and the exterior wall, packed with livestock, camels, horses, donkeys. This wasn't just a practical way to store animals. Every part of it was doing thermal work. The high exterior walls took the full force of the Siberian gales. No openings, no gaps, no corners for the wind to catch. The compound worked as one enormous wind baffle, a single massive barrier absorbing the wind's energy before it ever reached the courtyard. What got through was a fraction of what hit the outside. The livestock added something the walls couldn't provide: heat. A single camel generates significant body warmth. Multiply that across 20 camels, 10 horses, and 30 merchants inside a wind-shielded enclosure, and the courtyard air sits measurably warmer than the open desert outside the walls. Not dramatically, not enough to be comfortable without the Kang, but enough to raise the baseline, enough to give every other layer of the system a slightly easier job. Think of it as nesting. The compound shielded the courtyard. The courtyard shielded the room held the Kang held the merchant, 4 layers deep, each one a little warmer and stiller than the one outside it. The cold had to defeat all 4 to reach the person sleeping at the center. It rarely managed it. The animals weren't a winter inconvenience. They were heat sources, positioned in the outer ring where their warmth buffered the courtyard before the cold reached the rooms. Whether that was deliberate design or accumulated practical knowledge doesn't change the result. It worked. The compound held warmth. The Kang generated it. But what about the coldest hours, the window between 3 and 6 in the morning, when the fire had burned down to nothing and dawn was still hours away? The Kang was the primary heater, but it had one limitation. Once the fuel burned out, the stored heat in the brick began to fade, slowly. That was the point of the thermal mass, but steadily. By the deepest part of the night, the platform was still warm. but the air in the room had cooled, and the hours before dawn were when the desert hit its lowest temperatures. For that window, the merchants used clay braziers, thick-walled ceramic stoves placed on or near the Kang platform, burning small amounts of dense charcoal. The clay walls regulated the burn. The charcoal couldn't flare and exhaust itself quickly. The ceramic absorbed the heat and released it as a slow, steady radiation across the sleeping area. A small amount of fuel, hours of low-level warmth. This wasn't about heating the room. The room was already as warm as the Kang could make it. The brazier was about holding a survival pocket through the hours when everything else was at its weakest, keeping the air around the sleeping platform above the point where the cold became dangerous. Wood was a luxury in the Turpan Basin. There were no forests. Every piece of timber was too valuable to burn. The charcoal came from whatever dense fuel was available, agricultural waste, compressed dung, scrub from the desert margins. The stoves were built around scarcity, small fuel load, maximum heat output, minimum waste. Picture a merchant at 4 in the morning. The room is cool, but not cold. The Kang beneath him still holds faint warmth from the evening fire. The clay brazier beside the platform glows a dull orange, steady and quiet. He pulls his blanket tighter and goes back to sleep. Outside, the Gobi is minus 20 degrees Celsius. The wind hasn't stopped since sunset. He doesn't know. He doesn't need to. The system is holding. 6 layers: walls, earth, wind baffles, underfloor heating, compound design and portable stoves. Together, they explain how the room stayed warm. But they don't explain something larger: how these cities existed at all in a desert that gets 15 millimeters of rain per year. The 7th layer answers that, and it has nothing to do with heat. Everything described so far depended on one thing holding together: the walls. And in the Turpan Basin, the walls had an enemy that had nothing to do with wind or cold. Desiccation. Drying out. The Gobi cold is a dry cold. The air holds almost no moisture. In those conditions, rammed earth walls don't just face cold, they face drying. Loess that loses its moisture becomes brittle. Brittle walls crack, cracks become gaps. Gaps let wind through. A wall with wind moving through it is no longer an insulator. It's a liability. The entire system, all 6 layers, could be undone by the walls simply drying out. The Karez system solved this, not by design, as a side effect. Underground aqueducts, hand-dug tunnels that collected snowmelt from the Tian Shan Mountains and delivered it by gravity to the oasis floor. No pumps, no surface canals that would evaporate in the Turpan heat. Just tunnels, running for kilometers beneath the desert, feeding water to a city that had no business surviving there. The total network once stretched over 5,000 kilometers, all underground, all gravity-fed, over 2,000 years old. Parts of it still running today. The primary purpose of the Karez was water supply, but its presence created something else. The oasis around Gaochang was slightly more humid than the surrounding desert, not dramatically, but enough to keep the rammed earth walls from drying to the point of brittleness. Enough to maintain the density that made them effective insulators. A dense, slightly moist wall holds heat and blocks wind. A dry, cracked wall does neither. The Karez didn't heat anything. It didn't block wind. What it did was preserve the ability of everything else to work. Without water, the walls crack. Without intact walls, the Kang heats a room full of gaps. Without sealed rooms, the compound's warmth bleeds out overnight. The Karez was the invisible foundation, the layer that kept all 6 layers above it in working condition. This is why Gaochang existed where it did. Not despite the desert, but because of one specific feature within it: an underground water system that made the loess workable, the walls durable, and the oasis livable. Remove the Karez, and the city doesn't survive a generation. Keep it running, and the city stands for centuries. 7 layers, each one solving a different problem, each one making the others more effective, and together they turned one of the harshest places on Earth into somewhere a merchant could sleep with his coat off, while the Gobi tried to freeze everything outside the walls. 7 layers, dirt walls that slowed the cold, sunken rooms that borrowed warmth from the earth, a screen wall that broke the wind before it could steal what had been built up, an underfloor heating system that kept a brick bed warm through the night, 12 centuries before the radiator existed, a compound that used the body heat of livestock as a thermal buffer, a clay stove that held the survival pocket through the coldest hours before dawn, and an underground water network that kept the walls from cracking apart and held the whole system together. None of it worked alone, all of it worked together. The proof is still standing in the Turpan Desert, rammed earth walls, 1,300 years old, in a climate that should have turned them to dust long ago. These people didn't just survive the desert, they understood it well enough to make it work for them. If you want to see how the same builders solved the opposite problem, surviving the 70 degrees Celsius summer heat in the same basin, using the same desert against itself, that story is next. Subscribe and it'll be there when you're ready.